cloud. Okay, and then hide. All right, so to get to this, you gotta know my name. So and then I don't think capital matters, but and then I think there's now quite a few Beaucages. Before there weren't, but anyway, if you put research, but so and then you click that, you can find this, and then there's just a bunch of classes here, and it's the one at the top. And then if you click that, you get to that. Is that okay with you? All right. You don't need to write anything down, right? Right. So anyway, so then this first chapter's thermodynamics. Click that, and there's a video here. These are like last year's videos. I'm gonna hide this. So if you click this, this is the last class. It's on YouTube. All right. So if you're all right, and then on YouTube, like if you're not a native English speaker or whatever, you can do you can translate it into whatever Arabic or anything you want, Hindi, anything, any language you want. I don't know if any of you guys. Actually, it looks like everyone's an English speaker. Basically, in the past, we've had guys from Iran or something, and they can translate into Farsi, whatever. So there's a way, there's some button here where you do like translate, and that seems to be helpful to some, or maybe you're Korean, and you can translate into Korean. You can translate, these are on YouTube, you can translate to Korean. Yep. Like it'll translate what I say into Korean. Have you done that before? I mean,
it is maybe you must.
It's pretty cool to do. I mean, you do it in YouTube. Just Google how to do it. I don't remember. It's probably in settings. What is it again?
The CC button next to the.
Okay. Oh, closed caption. All right. Click that. And then somehow you can pick Korean. It's not doing it. Anyway, see if you can do it. If you can't. All right. Am I doing something wrong?
I think it's in the settings. You click settings.
Okay.
And then it says
Subtitles.
Oh, I see subtitles on. And then there's a way you can get it into another language.
I don't think so. I don't think it's auto-generated.
You can't do it if it's auto-generated.
Okay. Is there something I have to do in YouTube?
You have to go in and put in like English, like type out English.
I did that.
Transcript.
Yeah.
And then YouTube will translate that. But if it's interpreting what you're saying, it won't translate.
Okay. All right. You guys know more than I do about it. So, all right. So there's no way I can do it unless I type it out.
Yeah.
It seems like it worked before, but anyway. All right. So maybe it doesn't. Anyway, so that's where the thing is. It'll just be right there. And then the PowerPoint's here. So everything's kind of in one place, and the homework's like down at the bottom. You know, if you're on an iPhone, you have to go down, spool down, but for this, you just click that. Like this is this week's homework. All right. Is that everyone okay with that? Or right? So anyway, so I had there were a couple questions last time, so I wanted to go through those that came after class. You know, so I wanted to use this thing. It works. So one was all right, so we have like, all right, so you have this. So this you should memorize, like that square thing. So it has all the, like, so the definition. So that question was like dg equals minus s dt plus v dp, which you get from g, and then minus s dt, and then v dp. So you go like, get that, right? So one question is like, where did that come from? That's the kind of question. And then the second question about that was like entropies. Let's see, is this thing messing up? Or I think whoever's signed in, you have to turn off your mic. All right, so the other thing is like, this is derivative of the energy, and this is like entropy, and you think of like G, S, H state functions, right? A for Helmholtz. so why is it this is derivative and that isn't, right? Yeah,
Not to answer the question,
Oh.
more of a, well, this is a question, the moss next to you, are you able to close those?
good point, yeah. Sorry about that. Oh, yeah, sorry. So that's okay. Is it better without this light or? I don't know. Anyway, oh, it is? All right. Let me see the way to turn those off. Anyway, that's one way to turn them off there. All right, so. All right, so we get, so the question is like, why is that derivative? That isn't derivative. So this is like energy. And this isn't energy. It's like energy would be S dt. So S is is it? This is intrinsic, and this is X, like extent. So in other words, if you add, so volume's extensive. In other words, if you add more, like how much you have matters. Like if you have twice as much volume, so but you don't have twice as much temperature, or you don't have twice as much pressure, right? So it's always going to be to get energy. So you need to have extensive and then the change in intensive, like force times distance gives energy, right? So force, you can have a different amount of force, like you can have twice as much force, but you can't have so length is going to be kind of the intrinsic thing here for some reason. So anyway, that's basically how this works. So it's, let's see, volume. Anyway, force, forget about that. Anyway, so that's kind of why, even though these are state functions, this isn't a derivative here. And the other one is like, where did that come from? So there's, you can get all the derivatives like h dh is v dp t ds plus t ds. Du is minus p dv plus t ds. Right, so you can get all from all the four and derivative equations from this, and they come from, so the definition of G, to get the definitions, you go like G equals H and then ST. So it's minus ST. So the first time you see it, it takes the minus. If you use it the second time, it isn't the minus. That's kind of a nuance to this. So that's a definition. That's the definition of G. So if you do dg is dh minus s dt minus t ds, so derivative first times second, second times first. And then you use another definition for h. So h is u vp. So definition of h is, so h is u is u vp. Right? U plus VP, because the negatives on the second term, you don't use it. You only use it on the first, right? So otherwise, I mean, if you try to memorize all these equations, it's not possible. I mean, it's possible, but it's going to be painful, and you'll forget them like quickly because you won't use them all the time. So if you use them all the time, it's all right, but otherwise, this is a great way to do it. So PdV, right? And then you have, we had the du. So this is kind of the second law. So du is dw plus dq, and the kind of the second law part of this is dq is t ds, because we said that heat isn't a state function, but S is. You have this idea, if you take Q and divide it by T, then you can get the S from it, right? So that's the second law. So you have that term, and then the dW is PdV, right, which we had somewhere else. But so if you use that U in this H, then the PdVs cancel out, or it's minus PdV. And then you have DH equals TDS plus BDP, and if you park that DH back in this guy, the TDS, let's see, the TDS part cancels out, and then you have SDT and VDP, which is what you had, VDP, SDT is DG. Right, so anyway, that's So all these derivatives, so you can do that for each one of these from the basic definitions. This is just the definition of G, definition of H. So those are just kind of defined. It was just, you needed it, so you just made it up. And then this is the equation, like the parent equation of what internal energy is. And then second law gives you the Q part, and then it'll fall into this thing. Right. So, I mean, you're not going to do that every time you need a derivative. So this square thing will give that to you, like dg's s dt minus s dt v dp. Right, and then you get all the other derivative equations from that. And the same way, like this, so this has the definitions, it's got all the derivative equations, and it's also got the Maxwell equation. So you go, Maxwell's, you make like a horseshoe. So you go S, so if you have ds, dp, and they're both negative, so they cancel out, a constant t, that's going to be equal to SUV, like dv, dgt, dt, constant p. And these are all, that's positive, positive, and then the whole the p doesn't matter. Right? Yeah.
What is the chart called?
It's called the thermodynamic square. And some people look at it poorly, you know, because it's kind of cheating. But basically you can't remember. I mean, you can also, last time I kind of derived one of the Maxwell equations, but you can derive all of them also if you want to. But basically they're all in the square. So those are the three things. You can get the basic definitions, you can get these derivative equations, and then you can get the Maxwells. And with those three things, you can kind of calculate anything you want. So if you're in a crunch and you need to say, like, I got entropy and pressure, I don't want to get rid of entropy. I want things I can measure, like volume, temperature, pressure. This is how you transform it through the Maxwell equation. And you aren't going to derive it every time you use it. See, the square can give you those equations if you need them, but yeah.
So the subscripts on the one you just wrote for CMT, does that mean for constant?
Right, that's to hold it. Yeah, that's the standard way to say, like, it's holding that parameter. So hopefully that's okay. So that explains, that tries to explain, like, where did that come from? And also, like, why is this S and that's D here? Because it's energy, and then if it's going to be something that's extensive, then it has to have an intensive times it to get the energy. So energy is the thing that doesn't have a partner. So in the corners, in the middles, you have enthalpy, Helmholtz free energy, internal energy, Gibbs free energy. So those are the energies, they don't need a partner. And all the ones in the corners need a partner because it'll be extensive, intensive. Right. So in fact, there's just two. So it's like, so there's two here. But all right, so there's two there for the basic fundamental universe, right? But if you want to go to the real world, then you're going to be talking about, like, let's see. So you'll be talking about magnetic systems. You want to know, like, you have a nanoparticle. You want to know how the particle size affects the magnetic field of a nanoparticle. Or you want to know, like, how does it, you're using those for a battery, and there's an electric potential that's being developed. You're going to either use a nanoparticle silicon in the device, or you're going to use, like, bulk silicon, and which one's going to be better, which has a better potential, right? So this is intensive, extensive, but it's in terms of potential and charge. For a battery, for a capacitor, it's field and polarization, and for a magnetic field and magnetization. And just add in these terms to the energy. I mean, because usually you're just assuming that those don't exist, right? So that's for one material and one phase. So you have just, in this case, I just have water or something, or silicon. I just have the one thing, right? So if you want to deal with more than one phase or more than one material, you have a mixture of two, or you have water and water vapor, or water and ice, right? Then you have to include the chemical potential of the phases in the different, either in the material, in the different phases. If you have a binary mixture, say, like A and B in the liquid and the vapor phase, so it has a chemical potential of A in the liquid, a chemical potential of A in the vapor, chemical potential of B in the liquid, chemical potential of B in the vapor. And those, if it's at equilibrium, so it's sitting at the table, the chemical potentials of those components have to be the same in the two phases if they're in equilibrium with each other. Right, so the chemical potential also just adds into the free energy. So that's going to be the derivative of the free energy versus the number of atoms or molecules or whatever it is you're talking about. So if you take one out, how does the free energy of that phase change? Right, so take one out, that's the chemical potential of that thing in that phase. And if you have like a glass of water and a vapor above it, it has to be that if the water atom jumps into the vapor, if they're at equilibrium, it has to be just as happy to jump back into the liquid. So if you take one out of the liquid and take one out of the vapor, it's got to be the same because they're at equilibrium. So that means that the chemical potential and the liquid and the vapor have to be the same. So if you have, say you have ice, like you get a crushed ice in a drink, right? It's almost at absolute zero. So the water, it's like jumping from the liquid to the crystal all the time. It doesn't matter. It doesn't have any choice about being in the crystal or being in the liquid. It's just as happy in either one. And it, due to thermal fluctuations, jumping back and forth, right? So that's why the ice, like, so the only weird thing in that system is that it has a surface area and it wants to get rid of the surface area. Like it wants to remove it. So that's why the ice will just form a giant chunk eventually. Like it just wants to get rid of the surface area. It's constantly hopping back and forth. Eventually it'll just form this chunk, right? So anyway, so that brings up the idea of like what happens if you talk about small particles, right? So this kind of, so you just add, all you're doing is adding terms to the free energy to do this stuff. So you have so let's see, this surface thing is like great. So we'll do a whole chapter on surface stuff, but I'm just mentioning this now because this is definitely something that you should know from some point. But anyway, so you have the standard free energy, and this say you're dealing with different size particles, like nanoparticles, bulk particles, like a brick of the earth, right? Different size things. So generally, if you write this equation like G, so this is just the definition, G H minus TS, 20 square, you can get that, right? So for the change in the melting point, delta G, so as you melt the material and go from liquid to solid, there's a change in the free energy. It's going to be the change in enthalpy, change in entropy, times its temperature. This is for an infinite crystal. Let's call that T infinity, right? And if it's at equilibrium, so you're right where the ice and the water are just balanced out, it's at 0 degrees C, then that equals 0. From that, you can define what that equilibrium temperature is. It's going to be the enthalpy divided by the entropy, right? Because the free energy change is 0 when you're at equilibrium, so then that thing has to be that ratio. Right? So this is due to Gibbs. You know, Gibbs was a guy from he was at Yale. He was the first guy to get a PhD in engineering or something, I think, in the world or maybe in the US. But anyway, he was the guy that invented like half of thermodynamics, mostly the nanomaterial stuff. So anyway, in the 1870s, I think, something like that. So anyway, so basically he came up with this idea that you have the free energy and then you can add in terms to it. Like he came up with that whole concept, this idea, like you're going to add in the magnetization and the electric field. And one of the first things he did was like the surface. So if you have, these are bulk terms, you say like the specific free energy times the volume, and then enthalpy specific, it's like per mole or per cubic, whatever, times the volume. And then the surface term is going to be times the area. Right, so you can see volume is something like size cubed, and area is something like size squared. So this thing, if this thing equals 0, you're going to get a size out of this. Right, and that means if there's a temperature here of that thing at that size, that temperature is going to be different than this T infinity temperature because this thing has to balance out. So if you balance this thing out, you'll find out that size is this dependence on that temperature. Like the temperature becomes a unitless number divided by the infinite temperature, like 273 for water. These all have to be in Kelvin. Like you can't, anytime you're doing thermo, you have to have like absolute temperature. Don't do like centigrade. Right. So anyway, so that's how that works. Like the smaller the particle, so So basically you want to know like when does the thing melt? Like if I make a nanoparticle, it's going to melt sooner or later. Like it's going to be more stable, less stable, it's less stable, which isn't a big surprise. So you're going to have a lower melting temperature. So you have the infinite, the 0 degrees times 1 minus this ratio between the surface and the bulk. Yeah.
So for the surface, which and I'm thinking more of the area of the outside area that affects the inside area. Will we do the outside area affecting inside area or the other way around? So we do it as like the chemistry way where the object, the particle is the constant or the other way around based off of this part.
All of the above. So it's like 3 kinds of interfaces.
Yeah.
So there's, you can just say there's an interface and it's like a delta function. Then you can have a gradient. That's the second option. The third option is you can say there's an interfacial phase. Like you have a phase that's the interface.
Yeah.
And that thing has thermodynamic properties. Right. So I think you're thinking along the lines maybe of the last one, that there's an interfacial phase and it's got an inner and an outer.
Okay.
Right. So here, I mean, that's part of it. You can do that with this also. We'll go through that. We'll have a whole chapter on surfaces, nanoparticles. But basically, this is the general theme. And this is the number one definition, is just a line. It's a delta function. And if there's an energy associated with that delta function spot. It's a good question. I mean, there's a lot of different ways. There isn't one right answer to anything, you know. So in the thermodynamics, it comes off like this is just this one answer. Some of the things there is one answer, but generally there's a lot of answers. Right. So anyway, so yeah, so there's that comes out that you reduce the temperature, and it's got to do with the size. So the smaller the size, the bigger this negative term, this divided, so it's a denominator, and then basically you drop the temperature with the size. Melting temperature. So it melts easier when it gets smaller. That's what you might assume. But this equation gives you the idea, like, what do you plot? So normally you'd plot like temperature versus size. And you can find many papers that do this. Okay, so it's not just you that would think that way. Like, I measure the temperature, I have the size, I'm going to plot temperature against size. And that's not right, because what you should plot is a reduced temperature versus the inverse size. Like from this equation is 1 over size. So to make it a straight line, you need to plot 1 over size as the x-axis.
So,
Yeah.
explain this with a hard for me. Can I ask about the first equation at the second chapter? What's that mean?
First equation, this equation. Okay, that's just saying that these are bulk terms. Okay, this is free energy per mole, say, at a constant density. So it ends up free energy per volume. Right. So these are volumetric terms. So you need to, if you want to compare it with surface terms, you have to multiply by the volume to get the real number, the actual value for the free energy, not the specific free energy, but the actual free energy. Say you have so much free energy per meter cubed.
Free energy of what?
Of free energy change on going through melting. The free energy change.
Point melting.
Yeah, the change with melting. Yeah. So the difference between the liquid and the crystal.
And I wonder the point sigma A, why is that appear when related to
This because sigma times A is an energy. It's just the same kind of energy. So it's just an energy term. Like the surface energy times the area gives you an energy. That's the energy of the surface.
The energy which binds the atoms of the surface together.
Yes. So the surface has an energy higher than the bulk. Right, because it's the atoms are under tension. Mhm. Yeah, so there's an excess energy due to the surface. I mean, you can look that number up. It's in tables. All right, but because it's volume and area, then you end up with a size from that. And that size is the size of the particle. And if it's a spherical particle, say, I mean, it's just arbitrary cubed squared here. So I mean, you can put in the actual dimensions of the shape of the thing if you want. All right, so you can add in terms to these free energy expressions, right? And then set equal to 0 at the equilibrium, and you can solve for stuff. So you can solve for any of the things in that table, like all the electric polarization, charge for battery, magnet, you know, if you're dealing with magnetism, surface tension, right? So this is a way to go look at complex systems. Put in the say you have nanoparticles and you want to know, you can calculate the surface pressure of the particle, and you could calculate, say, the chemical potential of the species and how they would segregate to the surface. And there's a lot of things people do, but basically, so the easiest thing isn't to look at it generically. The easiest thing is take it from specifics, you know, like each specific application, and then figure out how this thing fits together. So that's kind of at least what we're trying to do in here. Then this is kind of the same business about state functions and how you can take different paths. I mentioned that before about Hess's law. Take different pathways to get to the same kind of answer. You know, you could go through that. What else? And that's if you do chemical engineering, that's like, this is the steam table. So you pick out the different, say you have one condition and you want to know, then you transform it to another condition. You subtract the enthalpies to get the enthalpy change in the process. And that will give you like the work and things, right? So if you did chemical engineering thermal, you would have done that quite a bit. Let's see. This thing, I think I went through that. This I didn't go through. So basically this is just showing. So if you plot, so for CP, right? CP is DH dt, right? Whatever that is. Here, so CP is DH dt, a constant P. So if you plot the enthalpy as a function of temperature, you should get a straight line if it's a constant heat capacity. Right, so you start with a vapor, it's got a certain heat capacity, then you go to a liquid, it's got a heat capacity, and you have a solid. So and all these lines will have different slopes, right? So then when you get to a transition, so a first order transition, first order means the first derivative of the free energy, or the first derivative of the enthalpy in this case, has a discrete change. That's called a first order transition. Maybe you've heard of that before. So the enthalpy, the entropy, the free energy all have a discrete change in the density. So all the state functions have a discrete change at this. So the first derivative of it isn't defined. In other words, if it's just a step function, the derivative is infinity. Right. So
you mean explain about the delta FUS? What's that mean?
this is the enthalpy relative, because you can't measure an absolute free energy and you can't measure an absolute enthalpy. So you have to go to a reference state. So say 298, 1 atmosphere pressure. Right. And you say there's an enthalpy for that. And then wherever you are in temperature, it's relative to that point. In other words, when this reaches, see, this is at like 273 because the enthalpy reaches 0 at that point. So the delta H is 0 for that 273.
I mean, at your side, the delta VAT, I know that that means the vapor, and then at the downward, the
Right.
delta fusion.
Oh, fusion, melting, yeah,
Melting.
melting, like crystal. So it's a crystal down here, it's a liquid, it's a vapor. Yeah, crystal, liquid, vapor. Is that okay?
Yeah.
Right. Anyway, so the point is like a first order transition, because this week's homework is about a first order transition. So that's what a first order transition is. The other option is second order transition. Okay, so second order transition is like a glass transition or some other magnetic transitions. In that case, you don't have the first derivative isn't a delta function. It'll be like a continuous change through this. And so you'll see a change in slope, not a delta function. And so the heat capacity is different at the beginning and the end. So these slopes, the way this is drawn, it looks like they're the same slope, but it's a different heat capacity for the vapor liquid, and gas. So they all have a different slope, even though you can't exactly see it here. So if it's a second order transition, it's just a change in slope. There's no enthalpy of glass transition. There's no enthalpy change at the glass transition. Right. So, yeah.
For second order?
What?
Sorry, for second order?
For second order, there's just going to be a change in slope and no delta. So there's no heat of glass transition. Because if you think about it, like say the things are just moving around randomly in a liquid state, and then they suddenly stick together and they can't move anymore. So heat capacity is how the material can accommodate adding energy to it through motion. Right, so the things can't move, then it's got to have a lower heat capacity once they get stuck. But there's no enthalpy involved in that. In other words, once you just get to a certain temperature, then they just release. Right. Whereas if it's a melting point, they're arranged, so the potential between the atoms gets changed when it goes through it. Like all of a sudden they aren't having the same associations. So you could take a box with the atoms and they all have these potentials with each other. And you could sum those all up and get the energy in that box, right? The enthalpy of the material in the box, sum up all the bonds. But once you go through the melting point, then they move around randomly, then the separation distance isn't that fixed distance anymore. Then the summed enthalpy will be different, right? And also because the thermal motion of things changes from when they're fixed in position to when they're moving around, the heat capacity changes because their ability to accommodate energy is different when they're in the different states, right? So anyway, there's a basic difference. And all right, so defining whether the transition you're looking at is first order or second order is like one of the main things people talk about and argue about, you know, because a lot of times it's things like what do they call it? You know, you're stuck, and then there's the thing is stuck, and then you go above the glass transition, and suddenly the release, right? And that action of releasing can lead to something that looks like an enthalpy of a transition. So usually that happens. It's a hindered motion, so it's stuck. So you can get a super cool liquid, then it can pop and kind of look like it's got an enthalpy. So there's a lot of, like, you can imagine people argue about this kind of thing, where they get stuck in some area. So anyway, so there's that business. All right. What else do we need to say here before I go to that paper? There was one other thing. All right, there's one other question that I forgot to say. So that there was that question. This from last time. The person that was offline asked. There was somebody that's in someplace, not in the U.S., that had some family stuff, so couldn't make it back. But the question was about absolute zero. Like I said, something like you have atoms moving around all the time, and there's different velocity atoms all over the place. And the question was, could the atoms like go below absolute zero? Like the question was about absolute zero, right? Oh, was it you that
No,
asked?
okay, I was gonna ask, I thought that was impossible. If you go below absolute zero,
Right.
they stop having a frequency and it just disappears from existence or something, like something crazy.
Yeah, maybe. Anyway, there's a couple of answers to it. That's good. I like that answer. That's pretty good. So if you say anyway, I thought I would answer it. You know, so you have like energy is kT. Or say you have one atom, right? Energy is 3F kT, which you can get this from kinetic theory of gases or Wikipedia if you want. And then that's going to be, for that atom, it's got kinetic energy, like 1/2 mv squared, right? So it's just what you're saying, like, that's the basic thing. Like if the thing stops moving, then temperature is 0, right? So you can't go, because this is squared. So velocity is a vector. It can be like plus and minus. But velocity squared is a scalar, and it can't go below 0 because it's a scalar. If it was, you'd have like -1 square root to get the velocity, and that'd be an imaginary number, so that doesn't work. Right, so just from kinetic theory of gases, you can't go below absolute 0. That's one thing. And then kind of the issue is this business that oh, where is this thing? So That's good. I want the wiki page for this. Okay. So this is what it looks like. You say that what's the probability? So these are for some places it gives for different materials here. So it's like for different materials at a given temperature, or this is at room temperature. So what's the probability that your particle is going to have speed of whatever, right? So so speed is temperature here. Square of that is going to be the temperature times a constant, right? So this is what the actual distribution looks like. Like if you have a huge population of heliums or xenons, that's what the distribution of the velocities will look like. You notice it doesn't go below zero. Like it can't go below zero because of that reason, right? That it's velocity squared, you get an imaginary number. So what is this distribution though of the velocities of things? That turns out to be kind of important. We'll talk about it more, but basically it's right here. So the distribution is going to be proportional to the velocity itself squared. So scalar again. And then it's got this kind of Gaussian term. So Gaussian means something squared, right? That you have an exponential minus something squared. That would be like a bell-shaped curve, right? So the reason you can't, and normally things are randomly distributed like a bell-shaped curve, right? But the problem with that kind of distribution, if you did that on this plot, say you have this velocity and it was a bell-shaped curve, well, you would have negative velocities, right? Because a bell-shaped curve doesn't know anything about zero, right? So it can't be that function, even though that would be your first guess. Like, what is the distribution of velocities? It's Gaussian, so, but it can't be. So it has to have this argument in front. So it's called the Maxwell-Boltzmann distribution. So we'll use that quite a bit later. If you want to calculate heat capacity, which means the ability of the material to store velocity, you need to know the density of states, which is the probability of finding something that has a certain velocity or energy, right? So this is kind of a mapping of what that looks like statistically. In actuality, it looks like this. I mean, at least in 2D. So it's this thing, imagine in 3D, that's what temperature looks like. So if you think velocity, the square of the velocity each of these things is the temperature. You can see some of them are moving kind of slowly, like those guys, and some of them are whipping across. You can find a few. So there's this distribution of temperatures. And that's what the basis of thermodynamics is the motion of these things randomly by KT, summing up into these values that you see, like the temperature, the average temperature in the room. So any point in the room, there's going to be some place where that atom is almost stopped, and that's really cold. Right? And there's going to be some place where it's moving like crazy, and that's really hot. But because like you can't sense that, right? They average out to what the temperature in the room is. But the molecules see that, so you have to kind of accommodate that distribution when you consider heat capacity and things. Okay, so that's partly what. All right, so we'll talk about that later on too. Anyway, so what else is in here? I talked a little bit about that. Oh, the Gibbs-Duhem equation. So this looks like this is like the most mysterious of the things here. So, and usually, like in the past, I've done a homework on this, and it's kind of useful just to see like how it could possibly be used. Because when you first see it, you think like this has absolutely no use. But so the use of it is that so if you have a system that's got multi-phases, then you add in this some else there, or is it? I don't see it anymore. It clicks, but it doesn't do anything. I think I'm still in project here. Oh, shows up here. I'm still in project. That's a problem. Yeah. So anyway, so you have the derivative of the free energy that we got at the beginning, and the add in this term is going to be the chemical potential of each of the. In this case, say it's just water and water vapor. It would be like water and liquid, and then water and vapor. So it'd be two chemical potentials, right? But if it's a binary system, A and B, so this is A and B, then you'd have the chemical potential of water in liquid state and water in the vapor state, and the chemical potential of ethanol in the liquid state and ethanol in the vapor state. right? So each one would have a chemical potential. So if you're talking about just the liquid state, it's water plus ethanol times how many waters times how many ethanols. Sum that up. And if you want to know the change in the free energy, it's that chemical potential, which is a derivative of the free energy with respect to taking one of the things out, right? Gives that, just that sums in as a term. Okay, so if you, all right, so if you say it's at equilibrium, delta G is 0, then this whole thing is 0. So if you have, so you can say like in the constant T and P, then you just have this sum of these derivatives. The sum of this thing is equal to 0. So you can say like, so you can say this sum is 0, right, at equilibrium, if you have constant T and P, because the first two terms drop out. And then you can, no, the sum of these things is 0. Let's see, constant T and P, that equals that. And then, let's see, how did I do this? Oh, I didn't do this right. So you have to say, geez, the sum of the atoms, sum of the number of atoms times the chemical potential. Take the derivative, you get the derivative of chemical potential, derivative of the number, derivative of the chemical potential. So you have 4 terms, right? And then you have this expression. You also have this expression, which is just the derivative, right? So there's 2 expressions. One's the thing, and dg also has to be this thing. And then by equating those 2, you can end up saying that the sum of the number times the derivative of the chemical potential is 0. And if you plug that back in with the SVV term, then you can get this expression. So basically with this expression, looks like it's kind of useless, right? So it kind of looks like, I don't know why this is so big. Did I expand it or something? No, that was the wrong thing to do. It was off scale, but so the question is like, where do you use this thing? So if you want to know, say you have a binary, so this is like you have a binary solid of nanoparticles, and then you want to know what's the distribution of the composition at the interface when the interface has a pressure that you can calculate. So you can calculate the pressure at the interface. So if you can calculate the pressure, then you can calculate the composition. If you calculate the composition, you get the chemical potential. From the chemical potential, you can tell the electrical properties of the material. So people use this Gibbs-Duhem equation to figure out, because you can write an equation of state for the G, and from G you can get the chemical potential. So you can calculate analytically the chemical potential, and then you can also analytically calculate, in this case, the pressure. And if you're at isothermal, then you can get basically, if you add in the term for the electrical contribution to this, the polarization, you can get the electrical properties of the system from that, right, from a nanoparticle. So this, anyway, it is not simple like how this is applied, but basically people always go through the Gibbs-Duhem equation. They don't say like why do you use it. Why don't I just leave that there? Because we're not going to use it actually later. So basically it's here. I'm probably not going to, we did a homework on this before, but I'm not going to do it this year. So let's leave that there. So I want to go, I'm going to bury that. I want to go to the to this thing. Get rid of this. Right. I'm going to go through the homework here. What that is. Gibbs-Duhem. Here's the homework. All right, so it's based on this paper. So this is a, oops, all right. This computer's got a mind of its own here. All right, so it's a Nature paper. So Nature is like the top journal, but it's also supposed to be something that's readable to people. So theoretically, everyone should be able to read a Nature paper, but it isn't always the case, right? So this paper goes back to this reference 7, right? He cites it, this paper. So sometimes you have to read the whole thing. So So this guy, Stanley's a pretty famous character. He founded this BU kind of colloid science department, which became like he became like one of the most famous people in the US, right, for kind of colloid science things. Anyway, so if you're dealing with biology, then water is important, like the structure of water particularly, and the weirdest thing about water is that the ice floats, right, because the solid state is less dense than the liquid state. So that's like an odd thing. It's a unique feature. So Stanley had this proposition that the reason that happened is that you have in the liquid state, it's actually got two states, like a high density water and a low density water. So there's actually two phases in the liquid state, liquid water, right? So, and because of that, because there's a spinodal for those two, that can predict that the density of the solid state is going to be less than the liquid state. All right, and then he didn't say why. He just said this could explain like what's going on in it by doing measurements. So then like the question is like why is that? Is there some kind of structural picture that you can get, like a cartoon that would say like why that happens? You know, so like this paper I think has like 500 citations. This is pretty decently cited. There's a lot of people that have looked at that subject. So these guys come in and say, well, let's just deal with a simple system. So water is known to form tetrahedron associations. Like you have a polar group, OH, and kind of a less polar H, right? So those will organize themselves into a tetrahedron, basically like a tripod with a flagpole on it structure. Right? So anyway, so and the ends of the tetrahedra can bond. So it's because there's a polar and non-polar parts to it that they make this kind of association. So he could make kind of little balls. Right, so these are, when people actually make these out of nanoparticles, they call them Janus particles. So it's a particle that's got different functionality, and so you can put like say you can put nanoparticles, they segregate to an interface, and you could blast it with a plasma or something. Then one side of the particle is going to be polar or hydrophilic, the other side's hydrophobic. Then if you put those particles into like hydrogen peroxide, they'll like move around. Then they'll also associate, they'll flop. You can make them do all kinds of weird things. So people are interested in particles like this, just generically, because you can make them do weird things. There's no device that uses Janus particles, but there's a whole group of, probably in the world, maybe like 5,000 scientists working on Janus particles, and there's no product. Okay, so it's like physicsy, but right. So the simulation people can do this pretty easily. Like they can just make a ball and then have different affinities on the surface of the ball. And then, so it can make it attract and repel, right? So he has like an A zone and a B zone, and then it can self-assemble into these tetrahedra that look like water. And then it comes to the question, like, if these self-assemble into structures, right? And then what happens to those structures? So he can make these tetrahedra kind of end up forming loops and knots. So all kinds of different topological structures on a computer, you know. So he's doing this on a computer. And he's saying that this is why you would have a high density and a low density liquid state in order to explain like why ice floats on water. Yeah.
Is there a difference in changing and
Well, he shows, so he can show somewhere here, he shows the plot of thermal expansion coefficient, and he shows a plot of isothermal compressibility, and they both show a transition, wherever that is. Here, alpha is thermal expansion coefficient. So these are supposed to be like a spike when you get through a first order transition. And the heat capacity shows a spike. So he can measure, he can calculate these things. He explains how he calculates these things at the end, but it's kind of involved. And for the purposes of this homework, you don't need to really follow what he did, except that he's showing that it's a first order transition in these plots. Right, in other words, these are the derivatives, so they should show a delta function. They should go to infinity. They should go to infinity when you reach the transition point. And then like the CP should have one value at one side of it, another value at the other side, and in the middle, when you get to the transition, should shoot through the roof, like it should just go to infinity. So these things kind of do that. They pretty much do that. So he's showing that there's this transition, and it's also shown that there's coexistence between the phases when you're at different pressures. So you can change the pressure in the system. So he's doing computer simulations, and he's doing it with constant pressure. So he lets the volume change. So that's kind of a nuance to this thing. So he's doing a volume changing computer simulation. Yeah.
So, for this homework or article, that we're supposed to read, for the figures, are they stuff that we can easily comprehend? If not, can you go down if you meant?
Oh, down here?
Yeah.
Yeah.
Particularly this chart where it has the LDL and the HDL.
So it's a
for some
low
people-
density liquid and a high density liquid.
Yes, I was gonna say, so for some of these, it seems that it may be hard to understand, especially for the blue chart that goes into the green and into the yellow.
Wait, where? Down here?
Go over to your left.
Oh, this?
Yes.
Oh, okay. That's supposed to be easy to understand.
Okay.
That's just his graphic showing like what WR is. Like WR, if you change from this thing to that thing, like if you interconnect the loops together. I think his idea is that this would be denser than that. Like when you have, say, you have a bulk material made up of these, the bottom thing would be denser than the top thing. He has a high density liquid, a low density liquid. They're both liquid, but if you have a lot of these, and how many of these that you have, that could define what a dense state is. Like a difference between two states, like liquid, vapor. This is this loop versus that entangled loop. That's the idea. So in order to, he can quantify those loops by counting up. So he's got the position of every atom. He can write a program to figure out how many of those there are in this box he has of millions of atoms. Like how many of these different kinds of loops. So in the low density, he says there's not many of those loops, and in the high density is a lot of those loops. And that's why one is denser than the other thing. And that's why, basically why ice is less dense than water. Because water has more of these loops in it than the ice does. Because once you start, the argument is that once you form a crystal, then you have these tetrahedra and they're in fixed positions within the crystal. So there's no opportunity for any loops at all. You can't loop if they're all in fixed position. The only way to get loops is if they're randomized, and then they can kind of like you throw the wire on the floor, it's random, you go to pick it up and it's all entangled.
Yeah.
But if it's spaghetti in a box, it's crystallized, there's no entanglement, it just pours out.
And I know
Right, so-
properly reading the article, we'll probably find out, but what is the, what's another name for the loops?
He calls them, I don't, there's not a, this is something he's made up, you know. So there isn't like an answer exactly to that. It's his answer. This WR and LR, like there's other people that have written papers. It's RIF. Sounds like an old English word. I don't know exactly what that root was. You probably look it up, but and the other one is called network linking. That one's pretty easy. L. So RIF and linking. But these are just words. See, they're just, it's supposed to be like cutting edge nature. It isn't supposed to be like something that already has been done. So he's like saying like, this is how you could describe it. So he does this computer simulation. You can get this answer out of it. Right. So yeah.
At the figure 1A, I don't know the tetrahedral structure of the H2O. What means that the yellow O and red A part, and what is the B part?
Oh,
and
the
what
A
is
and B.
parts
Okay.
they attach together?
All right. A and B are just regions with different. So the part, say you have two balls and they're going to have a potential of interaction, right?
Yeah.
So his potential is a square well potential. It's on or off. Like, so as the particles approach each other, then it's on and they attract, and that's it. And then if they depart, then it's off. That's his only potential. And but the particles themselves, so it depends how you spin the particle around. Like if the North Pole comes to the North Pole, then you have a BB interaction. At the South Pole, goes to the South Pole, you have an AA interaction. And the AB interaction is 0 for him. There's no interaction AB. So because he has those choices in it, then he can make it, and you have to have, you notice like A has a certain kind of breadth to it, like it was dipped into the paint only so far. So that angle of dipping, that affects the whole assembly, as does the energy, this square well energy, like the just one number and one distance, and it's going to attract or repel. So it's a really simple thing. Like he's made it so simple.
And the second part is makes me complex. Why is the let's pass voltage together?
All right, so he plays around with how much red and how much blue and the energy. So he's got 4 parameters he's messing around with. How much red, how much blue, and the interaction BB and AA. So there's 4 things he changes, and he messes around with it till he gets a tetrahedron to come out of his computer simulation. He just gets, and finally he says in the methods, and then there's also a supplemental where he says like, oh, we found these numbers and that's how it worked. Then once they get tetrahedrons, so tetrahedrons are a requirement to be water. It has to form tetrahedron because that's what water does. Water forms tetrahedra. Even when it crystallizes, it forms tetrahedra. And when it's in liquid state, locally, it's got tetrahedra, right? So then those tetrahedra interact with each other somehow, and then they form, statistically, they form some of these things. Like not all of them form. So this is the population distribution of how many of those different things that show up in it. So you can have the computer calculate how many of those things. Then going through, that's going to define his transition. Like when he gets a lot of those, then it's a dense state. When he gets a few of those, it's a less dense state. And that's what he says is a first order transition. So this isn't subject to, this isn't fact, this is what this guy is saying. So you have to look at it and say, well, that sounds like that's ridiculous, or you can say like, well, yeah, I agree with that.
And
Right, so this isn't a textbook. This is like,
almost the curl case means the energy level.
I couldn't hear.
In this article, almost curl case means the energy level.
In this article, the case.
Curl case, it means red or blue.
Oh yeah.
Almost things means the energy level of that color.
Yeah, the energy. Yeah. So the simulation he's doing is called Monte Carlo, right? So what you do is you take a bunch of these spheres and you throw them in a box, right? And then you kind of like randomly move them. And in this case, you also have to spin them. So you kind of just randomly move and spin everything. So you have state A and state B, or O and N, he calls it, original and new, something. O and N, I think is what he calls it at the end. So, and then you can calculate, because you can calculate from the distance between B's, distance between A's, the potential energy of the system. So you can calculate the energy of the system because you know where all the particles are, you know which way they're spun around. You can figure out what the energy is. You can say, well, in doing that random motion of the whole system, did the energy of the system drop or go up? So this is modeling like KT moves the atoms around and also spins the atoms. So that's the KT randomization. Then you say like, well, then I have another state and it's got another energy. Well, the energy dropped. That's great. I'm keeping that state and I'm going to go to the next one and do that again. Then that time the energy went up. So normally you'd say, well, throw that one away. But with Monte Carlo, you don't throw away the one where it got worse. You say, basically, you calculate how bad it was. Then you do a Boltzmann calculation to get a probability. So you take the energy divided by KT, exponential minus energy by KT is a probability. And you measure that against some probability that you say I'm going to accept, like 2%. And then some of the ones that are bad you accept. And that allows the system to kind of go over energy barriers. Without that, you couldn't, in other words, if you got to an energy barrier and only accepted good, you would be stuck in the well. You could never get out. Right, but because you roll the dice when you get to a bad state, it's possible for you to go to a bad state and get to a better state. Right, so there's kind of a barrier, and you have to have, that's called Monte Carlo. So that's what he uses here. He uses 2 Monte Carlos. One's a potential energy, and one is a spinning thing. So he's got like 2 Monte Carlo things going on. So it's kind of complicated. We'll go through that again later on. But basically, that's from your perspective. It's just like his results are right. like it worked. He figured out how to reach equilibrium. That part's okay, because you don't have a mechanism to really critique that right now. But basically, it's showing like there's a first order here. So, I mean, he's got those features that show a first order, and then he comes to the conclusions somewhere that this can explain like how water. I think the last it was colloidal we've established, blah blah blah. Primarily, let's see, somebody says this is how water works. Temperature, somewhere at the end, he says that this basically explains like why solid water's less dense than liquid water. So that's kind of what this thing is. Let me see what I asked here. So define a state parameter, right? So that's going to be like density, enthalpy, entropy, right? So basically, the state parameters are things you can, how you're going to define what a state is. Like in other words, I have a liquid state, I have the vapor state. What is a state? Like you have to define it by these parameters. Like you say, liquid has a lower density than the solid. So that I could use a change in density is going to be the first order transition would be a step function in density when it crystallizes. Right? Or step function in enthalpy, it gives off heat when it melts. Right. So that kind of thing. So anyway, so then the question is like, well, once you can define what a state parameter is, and you need to have a discrete change in state parameters when you have a first order transition, which is what he's talking about, liquid transition. So the question is, open question, like is a topological feature like a knot, is that a state parameter? Like in other words, if your shoelace is open and floppy and then you tie a knot in it, is that a different state in terms of thermodynamics? Or is it the same state? Or if you take the cables and you throw them on the floor and they're entangled, then is that in a different state than it was when it was not entangled? No. So it's definitely like if you want to unentangle your cables, it's going to take energy to do that. So anyway, it's just a question, like what is it a state? There's not really a right answer to that. Wood Hess's law, in other words, is there any route you can go through to get from one to the other and you'd get the same state parameters? Like Hess's law would be like I could tie my shoe one way or it could randomly tie somehow. And is there some kind of parameter that you can say like at the beginning and the end is the same? You could take the difference, say there's a change in whatever that is. Yeah. What? Yeah, is it? Okay. I mean, it's an open question, I don't think there's an answer to it. It's just like to think about like what is the state function, for this in the context of this thing. I mean, he believes it is, and there's other papers too. There's some other papers in the that go through kind of whatever. So let's see. There's that paper, this paper, there's a couple other papers that talk about. So these are references that he gave. So I put them in here so you could, if you feel like looking at them. But basically there's other people that have looked at this question of is this a state? So he isn't inventing exactly this whole thing. What he's inventing is this idea that he can use these balls to talk about this question, and then so there's a few papers. Those are just citations that he gave that seem to be relevant to the thing that you might want to glance at. But anyway, so let me go back to him. I'll go back to this question. So demonstrates transition is first order. So he demonstrates that it's first order by his calculations. So this is just defining what a first order transition is. Like, in other words, he shows that. He shows the that there's a discrete change in these first derivatives. These are first derivatives. This is the first derivative of volume with temperature, and that shows a delta function. Or volume with pressure for isothermal compressibility, and this is volume with temperature for the thermal expansion. So that because the first derivative is not defined, then that means it would be a first order transition. Same with heat capacities derivative enthalpy, right, relative to temperature. So that should be not defined at the first order transition. So that's why, that's what he's arguing here. What else? Then water has a strange feature. Explain how. So second to last paragraph in conclusions, he says like kind of how this relates to water density, like kind of in this paragraph, I guess. He talks a little bit about, so you can kind of read that and figure out. Basically, the idea is that like because of this looping, you could get a more dense state. Right. So that's kind of the gist of it. But it's kind of hard to see that that's, I mean, you can argue it both ways, right? I mean, so the question is like, is that really how things should work, right? I mean, the difference, so he gives pretty strong support with this when he calculates the thermal expansion coefficient, right? So with the tying your shoe, like there's no real thermal expansion coefficient you can calculate. So there's some differences between like a simple view of this and what he did. Then there's these important questions, you know, like, has he reached equilibrium? Like, so any computer simulation, the first thing you have to say is like, did you reach equilibrium? And you can't answer that question because there's no way to tell that you've actually reached equilibrium. You can say like, you can plot out the density and it reaches a plateau. You can say, well, if I wait twice that long, then I've reached equilibrium. But you haven't actually proven that you've reached equilibrium. Like there's no way to actually prove it, right? So the same with this question of ergodic, like, right, ergodic in this case is a really interesting question to ask because he's talking about the thing locking in, right? Which is kind of what a glass does. So he's talking about topological knots forming that lock in the structures. So you would say inherently that's a non-ergodic system. So it's not subject to thermodynamic analysis. First off, so you can see like things, why these words show up to talk about things, right? So and then the question of, so the Boltzmann equation is in the notes, but I didn't mention it. But that's like the third, kind of the third thermodynamic law, right? Is you can calculate the entropies and the number of states. Like say you have like red and black marbles, and then if they're in a single state, so they're in a crystal, so they're arranged red, black, all red on the bottom, all black on the top. There's one state, ln of 1, 0, so there's no entropy. That system is a perfectly fixed system, right? And if you shake them up, there's a bunch of states. You can statistically calculate how many, and you can get the entropy from that, right? So this becomes like a way to calculate how things are going on. For this system, like if you say like if you start with this and go to that, like is it a different number of states? Like that's an open question. Like in other words, it looks like there's no entropy change between the two things. Like in other words, they have the same mobility or randomness in both cases. It's just the picture that you put on it. It's like you look up at the stars and you can see like Taurus or the Big Dipper, but the stars are random. Okay? So just because you see the Big Dipper doesn't mean that the stars have a different entropy from a random system. Right. So well, it's got to do with how many states. From Boltzmann's perspective, it's how many states it has. So the density isn't necessarily the key thing, you know. It's like the arrangement of it, like how could it be arranged differently? So it's got to do with the arrangement of the things. I don't think it's just the density. It's a good point. Like density changes, it should have a different entropy. That's a good point. But basically, I'm looking at it from a different way. Like you're putting your mind onto these things and saying, I can see this loop and that entanglement. Just because you see it doesn't mean thermodynamics sees it. You know, it isn't really a parameter that you're going to judge the thing by thermodynamically. It's something you could say, oh, I can identify that. And there's more of those here than there. But somehow there's something fishy about this whole thing, I think, to me, but like it seems to be a little bit made up. And remember, like you can't trust people, like especially scientists. Like if they want to see a transition, then they'll figure out a way to get a transition. Like even if they're showing a
Computing all this. Computer.
he's got the computer, he controls the computer. If he didn't get this answer, what would he have done? That's the question. Well, he'd go back and do it again until he got the answer. So in the sense, like, yeah, it's pretty definitive. He's got this first order transition, he shows the evidence. But if you go in actually and you look at how he calculates the thermal expansion, it's pretty hard to. He explains it at the bottom, actually the absolute bottom of this thing. It explains how he gets alpha, and it's mathematically really complicated. And I'm sure there's a lot of room for like messing around in this. So I think your gut feeling for it might be as valuable as the actual measurement that he shows, because if you look through like how he got the numbers, it's pretty complicated. Really. Well,
it's hard to do experiments. You just form ice so easily around the experiment.
Yeah.
Just,
Yeah. Anyway, it's something to think about. It's not, some of these things is not really a right or wrong answer. So if you if you guys get into trouble doing it, let me know and I can help you through it. That's probably the best bet. But otherwise, it's just theoretically like any nature paper you should be able to pick up and read it. So it isn't always the case, or if it looks interesting, you can at least like look at the references and figure out where they're coming from. Like yeah.
I had a question. It was from earlier, actually, when you were going over the movement of atoms and revolving around heat. And I wanted to know, so for different states, so for the sun, for instance, if when they collide, it's so hot that some of the molecular weight actually is lost, and that's how it gives off so much energy. For that state, like if that is like a different state, if the molecular weight is like diminished or it weighs less because of the heat transfer.
Well, options.
Yeah.
So I mean, I don't know, but I mean, the chemical reaction, so it's mostly, so you got to be careful. There's like thermodynamics and there's kinetics, right? So like separate subjects, and they tend to be like they tend to like overlap each other quite a bit. And sometimes you get into a problem where you're trying to talk about a kinetic system, and then you try to make it into thermodynamics. And it's better to try to draw a wall between those things, because it can be misleading to kind of look at the two together. In fact, the equations will be like the same equations. Like you can calculate the Laplace equation from either from a kinetic model or from a thermodynamic model, but it doesn't. Sometimes it's better to look at something one way or the other, and not to let them mix.
Yeah.
So the sun's like a kinetic system, I think, and I don't know. It's hard to define whether it's a fusion reaction, right? So hydrogen turns into helium, I think. So that's a transition, but it's kind of a kinetic thing going on, I guess. It's a nuclear reaction, uncontrolled kind of explosion. So, but if you take and just burn plastic or something like that, that's not a phase transition. That's a chemical reaction. Even though the beginning and end products are like solid and vapor. So it looks like it's a phase transition. But generally, you're talking about the same thing at the beginning and the end, the same material. It isn't like broken up. Yeah, I mean, you could look at this as like it's not the same material at the beginning and end either, because you form these knots and things, and it's almost looks like you denaturing a protein or something. Like you start with this fixed state and you end up with this other state. Could have something to do with the sun. It's possible. Hey, any other things, or kind of went through this stuff, but I guess am I early? I'm trying to figure out the timing of this class. 2:50 I'm supposed to go to, but I think we're kind of done today. Very much, but unless you guys, unless there's questions or something. We got 6 people missing, I guess. That's all right. I think we got people online, so it should work out okay. I mean, you don't need to come if you don't want to. Actually, I heard Kentucky schools are like shut down because of illness and stuff now, like COVID and flu and something else. So who knows? Might be good. Maybe we'll be wearing masks and it's hard to tell, but because they started school August 6th, and this is 20 days later, and they're shutting down because of illness. It's a climate change thing. Something's going on. But anyway, hopefully we won't get that, but all right, so yeah, that's about it today. Did everyone find their groups and everything for the, all right,
Yeah.
okay.
So maybe we'll both read it and then.
Can I see the PDF, PPT you, yeah, that, and then the part, so can I find?
Yeah, sure.
Yeah. So once we both read it.
This part, okay. I can't understand why is these are in the same state. At this point.
Yeah, so you have, all right, so we have, this is just a definition, like DG just add in the, this is the change with taking out one atom of I, right?
Yeah.
So times DI, so that has to be the free energy we get.
Yeah, I know this means, but I misunderstand. Complex is at the constant TMP. These are zero,
because it's,
right?
yeah, DT,
Yeah, these are zero.
DT, so those have to go to
And
zero.
also, at the next part, it also says constant CMP. These are zero. I don't know why is this like? Why is this like?
Oh, because G is this, right? G is
so
that.
G
That's the
and
definition.
So
And if you
G
take
and
the if you take the derivative of this, you have to do derivative first, derivative second. So you have to do, you get 2 terms, not 1. You have to take the derivative of the number also.
But in this equation, why is there no delta minus? Why these things are not here? Why this can be explained without these parts? It makes it complex.
This is just how they do this. Yeah, this is just how it's done in the textbook. So I don't really know why there's no TMP here. I can figure it out.
So
I can come next
and
time.
where can I see this PowerPoint?
Oh, you can see it just in the web page.
Web page?
That's right here. Just look at that. The first one is a PDF. That's a PDF, and the other one's a PowerPoint. There's 2 clicks, yeah.
And where can I see the corridor of this
The video's like right here.
This Tuesday, and this
That's
video
last
from the
that's from
Tuesday.
yesterday, yeah.
Yeah. And the video of this class will be inserted at
Yeah.
about five.
Yeah, yeah.
Okay. Thank you. And we have to complete the homework until
Monday,
next Monday, 11
Yeah.
GM.
in the morning, no, 11 noon,
Yeah, I know.
at noon, yeah, it's like greater in the afternoon.
Maybe I misunderstood. Is there any for this homework?
Yeah, it's a group homework,
Group homework?
so there should be three, at least 3 people. that
At least
do it.
3?
3 or 4,
I
yeah.
misunderstood. I should write that.
And then on Canvas or Canopy, you go in and find the group. Have you used that before?
No.
That's.
Yeah, sorry. Two ways to do it.
One submission up for the homework and for group.
One submission, you're right. Yeah, one submission.
So you can done instructor.
Yeah, that is high density.
So that's,
This is low density. Because we don't find any notes. And items are directly attached to this.
so that's why I think I was confused. So the
I
comment,
think this is just a simplification.
so that's what the comment, the caption in the article is talking about. This is only pertaining to high density.
Yeah, see, this is just that's what the molecules look like, or the balls look like, and the other one is a.
So-
Graphic interpretation.
So what it's saying is that number C, the caption says illustrative snapshots of theta curves found in the high density. So it's no low density.
Right, it's just showing this is what it would look like with the spheres, and that's what it kind of graphically looks like, you know.
So that's what he's assuming that with a low density, you are not seeing these knots. And then when it comes to high density,
Okay, well, there's some knots in both, so it's a probability.
okay.
There's some knots in the low density too, it's just there's more in the high density.
Yes.
And then,
That's also what's kind of wishy-washy about this thing.
that's what it is. I think
Yeah,
that's why it was hard
It's
to
pretty wishy-washy, yeah.
understand. And then you have, sorry, you probably said last soon. You say, question B demonstrates the figure transition is first order in figures, 1C through E.
Yeah.
You talked about how, figure 1, how,
So in a sense, in the class, you have explained that we could define.
Yeah,
first order
explained that
transition.
C. I'm curious how
Oh.
D and E explain first order transition.
Because there is no change in the area of those three graphs, so there is no changes.
What is density? So the density, you get a delta change in density. So it should just be a correct.
Okay, so direct change in density and then E.
When we can't find any changes, that could be the question.